here, these are called Pele's hair. They're these very thin, long filaments of lava. And these get formed in nature when lava has gone off of an edge, and then it's gotten picked up by the wind, so it's blown into these very thin strands here. In Icelandic, these would instead be called witches' hairs or nornahál. As you can see, they do cool off very, very quickly. They go from orange to black in just a matter of seconds. Because of how thin they are, that also does make these incredibly, incredibly fragile. Something this thin and small, being formed around an erupting volcano, is going to get destroyed immediately. So pretty difficult to actually find outside. The only way that we find these in nature is if they get kind of picked up by the wind some more and then blown to a separate location where you can find them. All right, so here is just a little bit more ice. So I'm going to put that on, let's see, right there. I'm just going to add a little bit of pressure on top of it. All right, so we got a bubble forming in the back here. We'll see how big it grows. You can see one kind of coming in on this side as well. All right, so what is happening at this point, if you notice at the surface of the lava, it has pretty much stopped moving entirely as it's already beginning to solidify. So now when I put this block of ice on, the lava is already too solid at the top, but it's not in the middle. So it's still a little bit gooey in the middle, but it's too hard. So when the steam tries to get up and out, it can't. So instead, it just blows the lava up, just like a balloon. Now, lava is an incredibly, incredibly good insulator of heat. So it creates its own insulation when it solidifies on the outside. So even though it has completely stopped moving at the surface, if I just flip that over, underneath you can still see it's flowing. It's still liquid out from right here. And I can still even make some hairs with it, despite being solid at the surface. As it just kind of spills out there. I can also even probably get into one of these bubbles here if I just break that and kind of dig into it just a little bit. So I can pull it up, but then as soon as I expose it up, you can see that it's already turning black, and then it's going to be a bit on the crunchy side now as I pull it up. That will insulating. It will also allow me to get underneath this part right here, where I can then begin to pull it. It is going to bend because the whole outside is now solid. It's still just that middle part that is going to be hot enough to stay liquid. And so it's going to bend, and then when I release it, it holds its shape because it is just beginning to solidify entirely now. So this process of how it's creating its own insulation like this is going to be the same process that in nature will cause a lava tunnel or a lava tube to be formed. So when you have what is called an effusive type of eruption, effusive being the opposite of explosive. So when you have an effusive eruption, you have the lava is going to be pouring out of the crater in these sort of rivers of lava that are going to be coming out of it. So these rivers are going to go through this same natural process where those rivers are going to cool on the outside first, and they create this layer and crust of insulation around it that allows that middle part of the river to continue to stay hot and molten for a longer period of time, so that that river can continue to flow and to move and to burn its way through the ground until eventually, when the volcano stops erupting, the liquid lava will evacuate itself out, and then what's left behind is that layer of insulation, which is what your lava tube is going to be. All right, so all of these lovely noises that you guys are hearing coming from this, that would be the expansion of the metal. So that slide is made out of steel. And so with the lava on it and everything, the steel is very, very hot, but it's not melting. And so it's actually just expanding. And so that's kind of what you're hearing. You're just hearing the expansion of the metal. And then these panels on the side here make it echo very, very loud. So that's what you're hearing. This gentle popping noise, though, that you're beginning to hear kind of near the base, near where the actual lava is, this kind of Rice Krispies pop rock sort of noise. So that noise is the lava actually contracting in on itself. So when lava becomes solid, it contracts and it shrinks in volume. So that's what all these tiny little noises are here. So I'm going to grab my temperature gun at this point now and give you guys a little reading of where we're at. So when it came into the room, it was 1,100 degrees Celsius or 2,000 degrees Fahrenheit. Wherever the ice is going to be the coolest part of it now. So we have dropped all the way down to a very chilly 400 degrees Celsius. That's about 750-ish Fahrenheit. We come up here, we're still up at 680 degrees Celsius. That's 1,260 degrees Fahrenheit. If I can get, let's see, inside of this bubble here, inside there, where it was covered, so it should have had a little bit of insulation. Yeah, so that one is also 670 degrees Celsius. And so, very, very fast. Oh, here is just a very small piece of paper, basically. Obviously, it catches on fire very, very fast. And that's what we call an actual lava lamp. So actually, how this is catching fire, just because it's so hot, even though we're not in a liquid state anymore. This is actually a very big problem that we're having out at our current eruption site, because the area is covered in moss, and right now it's the summertime. That moss is incredibly dry, and so even the parts that are not touching the liquid lava coming out of the volcano, the whole area is just catching fire. We're getting these horrible wildfires out there. That they're doing their best to try and stop, but yeah, everything, just the ground is so hot, everything is just lighting up on fire out there. Even last weekend, they had to close the eruption site for 4 days straight, just because of how bad the smoke was. It's very, very rare to get an actual wildfire here in Iceland. They don't have a lot of stuff to burn. So what does it sound like when I smash it up like that? Glass. Correct, because it is glass. This is volcanic glass. So it is going to be a little bit different than what a window is made out of. So volcanic glass, this is going to get formed when lava is cooled down really, really, really fast. So fast that there can be absolutely no time for any crystals to form. So there's no crystals in this lava. There has been zero crystallization happening. And so when lava doesn't crystallize because it's cooling too fast, what's happening is that all of the atoms and molecules that are making up what the lava is, when they're cooling down too fast, and they have to become a solid structure quickly, they're just going to grab onto whatever is right next to them, in order to be a solid right at that second. And so that's going to be the most readily available and abundant element they're going to bond onto. And in this case, that would be silica, because silica makes up 47% of this lava, so almost half is just silica. And so when everything else is bonded onto a silica, then everything ends up looking like silica. And silica is what your windows are made out of. And so that's how we're ending up with this glass, this volcanic glass. It's going to be really rapid cooling, no time for any crystallization, and everything has bonded onto a silica. Now, it is black, it is not clear like regular glass, and that's just because this is an impure form of it. We are only at 47% silica. We do still have 53% of what we would call impurities. And so impurities would be like, it'd be the iron and magnesium and calcium and the aluminum and just all the other stuff that's floating around in there, all the other elements. So we have an impure glass, so it's going to be black instead of actually clear. So I am going to pick up this piece now and then show everybody what the inside looks like. Alright, so I am going to hold it up to you for first. Black outer edge on it. That would be our initial cooling layer, so it's going to be insulating all of the heat inside, so that's why the center can be nice and red hot for a longer period of time. So anywhere that you're seeing on this lava that it is still red, that means that it's still above 600 degrees Celsius. Once we get below the point of 600 degrees, that's when we are going to start to lose that red glow, and it's going to just turn black instead. And so this is happening because, again, all of the molecules and atoms that make up what the lava is, when they are really, really hot, then there's a lot of energy in them, because that's what heat is. Heat is just a form of energy. And so just like us, when we have a lot of energy, atoms and molecules, they're going to be moving around to get rid of it. And so they're all really, really excited with all of this energy, and so they're bouncing around, they're kind of moving around like this, and they're just taking up tons of space, and they're releasing their energy, in the form of this light. So that's where we're getting this glow from. This is atoms and molecules that are moving around really, really fast because they're excited. And so that's only happening above 600 degrees. Once we get below that point of 600, everything is just kind of too cold. You're just not really going to get that type of excitement anymore. And everything is going to lose that glow. So this is the point where I do like to turn up the lights though, just here in the front, so that you guys can see how much it does look like glass. Also, I do think it's pretty. So do I have any questions? One of the dangers that I had mentioned about lava is that there's a lot of this toxic gas and fumes, all that sulfur dioxide, carbon monoxide, the hydrogen sulfide, everything, all of that stuff, all that nasty stuff. We don't have to worry about that in the room, clearly. You guys are all in here, and you're not dead, so that's good. And so it's because of the gases that are harmful in lava. Those are only actually coming out of the lava at the time of eruption from inside of the earth, because that is where the gases are coming from. They're coming from inside of the earth. And so once lava is making its way towards the surface and erupts itself, it's going to go through a process that's called degassing. The gases are coming out of the lava. Once the gases are up and out, because everything is unpressurized, the gases can't get back into the lava. There's no way to reincorporate toxic gas back into erupted lava. So once they're up and out, it's up and out forever. The source material for the lava we just poured is this sand right here. which was erupted out of Katla 104 years ago. So all those dangerous gases in it came out 104 years ago. So when we pick it up and then put it into the furnace to melt, there's nothing to be reincorporated back into it. So poured out, danger totally eliminated. Now this source material though, it's this black sand. And this is like the black sand beaches that we have on the south coast. And so how this was formed though, is in a very, very specific type of environment. And so this sand got formed inside of the crater of Katla when Katla was still erupting underneath its glacier. So when you have these sort of big glaciers on top of volcanoes and it starts erupting, it's generally not going to just be like, it immediately just bursts through the ice. There's going to be a little bit of time where it's just melting the glacier from underneath. Because the glacier on top of Katla, Miðdalsjökull, is very, very large, so it's going to be more than twice the size of the entire Reykjavík city. And the thickest part of it is 700 meters thick, or about 2,300 feet of ice. And so when Katla started erupting in 1918, first, the lava was just melting the glacier from the other side of it. Ice melts into water, water gets into the crater, where you get it interacting with the lava. When you have water and lava mixing under intense pressure like that, you are going to get these huge, giant steam explosions. And so that steam explosion is going to blast the lava apart into all of the lava sand here, this tephra, which is just a fancy geology word for sand. And so all of this tephra sand stuff, this is all going to be collected up in the crater until eventually the volcano is going to be able to break through the ice, and then you're going to get a glacial flood. These glacial floods are going to come crashing down. They're full of water and icebergs and all of this exploded lava. They make their way to the shoreline and they deposit, and then we get a black sand beach. And so that's where our black sand beaches are coming from. This is all just exploded lava from inside of a crater brought down by glacial flooding. And that's why also our black sand beaches are accompanied by like having really, really flat land. Because glacial floods are extraordinarily powerful. One, they're really, really heavy because they're full of stuff, but also the massive amount of water that's coming down is just insane. So it takes down roads, buildings, bridges, everything is basically just going to be completely flattened and washed away. So that's why we're also getting these black sand wastelands, especially east of the huge wasteland of just black sand. And so even though these two things are chemically identical from one another, this is exactly the same as that. Just different environments of formation are going to give two completely different looks from one another, despite being actually quite the same. Yeah? When this cools, do we recollect it to remelt it? Yes, we do. So we can reuse the lava. We can take that and we make it into smaller pieces once again, and we can throw it back into the furnace and remelt it, make new lava. So yes. And so that's why also, like, if you notice here with this part that I flipped up, all of this sand that sticks to the base, so that's also how we're reincorporating some new material every single time that we do it, so it keeps everything fresh and the chemical contents of how we want it to be. Yeah? What's the difference between magma and lava? Magma is when it's beneath the surface, and lava is as soon as it's reached the surface, as soon as it actually starts erupting out onto the ground.
And did the Vikings ever use volcanic glass anything?
The Vikings used volcanic glass for things. Yes, absolutely. They made a lot of weapons out of it because it is glass. You guys have probably heard of it, like obsidian weapons. Same thing. And so, yes, you can use this because it is very, very sharp. It is a form of glass, and so Vikings often made daggers, knives, not really swords. Swords is a little bit too long to make out of it, just kind of break. It is glass. There was this really fun weapon that Icelandic Vikings used to use that was essentially like a baseball bat with a bunch of glass stuck into it. So yeah, they had some pretty brutal weaponry made with this stuff.
Why does the moss like to grow in the lava fields?
Sorry?
Why does the moss like to grow in the lava fields?
Why does the moss like to grow in the lava fields? It's just because moss is just the most common type of plant here that we have. It's there are very few plants that can grow here. And moss is just one of them because it is just highly resilient. It can exist in extreme cold, and so it just likes the climate here. However, on lava fields, because lava fields take so long to cool down, the moss actually is going to take, on average, about 70 years to grow, to get to where it's at. And so that's why there's a lot of signs around ice saying stay off the moss, stay off that kind of stuff, because it takes so long for it to grow because it's so cold here, and for half the year we don't really have any sun, so it can't grow. So yeah, moss just likes it because it's really, really resilient to all sorts of things. Yeah?
At what temperature it starts becoming lava again this sun?
At what temperature does this start to become lava again? It's going to kind of start becoming melty around 900 degrees Celsius, between 900 and 1,000. And then at 1,100 we're going to get it's fully liquid. Yeah?
You mentioned crystallization and that it wasn't happening. What happens when it does crystallize?
Ooh, good question. What happens when it does crystallize? All right, so when it does start to crystallize, what you get is essentially, you're going to get kind of like more of the stony look, more of like what you just see outside. And so you could also just get big chunks of like, it's called feldspar, flagship-based feldspar. We have a lot of that crystals. And so you can start to see crystals. They're going to be kind of looking like quartz or calcite. We get a lot of that. Amethyst. So that's the kind of the crystal growth that we get here in Iceland. But actually, these columns here, around here, and all over Iceland, this is one of the fully crystallized versions of basalt. So this is what it looks like when it is fully crystallized. These are very, very small crystals. I will give you that, because they're hard to see with the naked eye. But if you had a microscope, it'd be very easy to see them. And so yes, this is one of the crystallized versions of basalt that we see here. Except that these columns, this is crystallized basalt actually that was cooled underground. So we're also going to get different looks of whether if it's cooled above ground or below ground. And so these columns here, so this is what happens when you give lava a longer time to cool off. So it does have that time to crystallize. So this is something that would be formed, I think the easiest example is like at the bottom of a lava lake, big lake of lava, at the bottom, because it's cooling down the slowest, and it's way underground, it's underneath all that stuff. And so when you're giving lava this much time to cool off, and I'm talking like hundreds of years worth of cooling off, all of those molecules and atoms, they don't just have to grab onto silica because it's the closest thing that's right there, and it just needs to become a solid in that second. If, let's just say for an example, I am just an atom of sodium. Say I am a sodium atom, and I get to float around in the lava for 500 years before I actually need to become solid. That means I have way more time to make more complex crystalline bonds with the other elements around me. So I can float around over here, and I can take some irons, and I can float around over here, and I can take some aluminums, and I can float around over here, and I can take some silica, but, you know. And so in this way, all of the elements can come together in these more complex, interesting ways, and create this crystalline sort of structure. And then because this is something that forms underground, you have the weight of all the stuff on top of it that's pushing down and adding pressure from above. So that is going to cause our crystallized lava to then break into these natural hexagons. Nature just decided that the hexagon was the best shape ever, I guess. So this is just nature that decides the hexagon. They don't necessarily have to be actually six-sided. I think the most sided one we have here in Iceland is 13 sides. I'm pretty sure Giant's Causeway has one that's like 16 or 18 sides or something like that. But the most common shape is going to be that hexagon. And so yeah, that's kind of what happens. That's what happens when it crystallizes underground. If it crystallizes above ground, you're just going to kind of get a regular looking rock. Yeah? Not hot at all. So because these are so thin, are less than a millimeter thick, I would say. So these cool off pretty much immediately. I could actually probably grab these with my bare hands just like 5 minutes after I actually created them. So yeah, the hairs cool down very, very quickly, so you can just grab them. However, these pieces right here, even though they are incredibly small, like even just, I have this chunk right here, so I kind of have this smaller chunk here that's still 200 degrees Celsius. On that, this piece up here in the slide, these are still 300 degrees Celsius. So yeah, the hairs cool off very, very quickly. The rest of it does not. Yeah?
When I took geology classes, they talked about gabbro, like BBA, like the slabs for like roofs and whatnot. Everything we've seen, we've been here for about a week, everything we've seen has been like basaltic columns and whatnot. Are there places of gabbro on Iceland?
All right, so she's asking about a rock called gabbro. So, gabbro is essentially, I mean, you guys have all heard of granite, correct? Granite, like a granite countertop. So gabbro is the granite equivalent if you have a basaltic lava. So if you have basalt, you can create gabbro. The problem with that is, so gabbro is incredibly chunky crystals. It's going to look like granite, just a different color. But, you know, where you have these big, big hunks of crystals in it, like big giant ones. And so we don't really see that here in Iceland. I do think that it does exist way deep in the middle, but it's incredibly rare because in order to get crystal chunks that big, things like granite, things like gabbro, to get a crystal that large, we're talking about a lot more cooling down than just a couple hundred years. That type of crystal growth is going to take several hundreds of thousands and millions of years. And so that's an incredibly long amount of time. Even the oldest parts of Iceland that are exposed above the water are only 3 million years old, which sounds like a lot, but it is not a lot when you put it against the geologic time scale. They're way too big. 3 million years is absolutely nothing. And so while we do see a very small bit of gabbro, it is incredibly rare just because Iceland is just not old enough to have created it yet. But yeah, maybe in a few more million years we're going to have some more. Alright, so they did open the doors for me, so that means I do have to give you my one last fun fact about lava. And that is that this stuff here is incredibly, incredibly heavy. This is 3 times denser than water. Because aside from silica, the next main ingredient in it is iron, at about 15% iron. And so 3 times denser than water. All of us in the room, the humans anyways, we are mostly made out of water. And so because of the density difference between us and that, it is physically impossible for us to sink in the lava. So if you do want to go visit our brand new eruption site, and you somehow fall into the crater of the volcano, you can be comforted in the fact that you will not be drowning in it. At the very least, no drowning in lava. I will say you have maybe 1 or 2 other problems on your hands, but you will not be drowning in it. And then now that you also know this fact, you can be the worst person in every room the next time you watch a movie, and explain how scientifically inaccurate anyone drowning in lava is going to be. So, yeah, that's Lord of the Rings, maybe. All right, and so with that, I would like to thank everybody so much for coming to the show. I did hope that you enjoyed it.